We have reached the last video. What a bittersweet story it is. All right, so our last video here, we're going to talk just a little bit more about these two spaces, and then we're going to talk about basically their definition in a linear transformation. So let's get into it. So here's this example. So I have, so here's my matrix A. I have a U and I have a V. So again, just to remind us, the null of A is the set of all x's that satisfy ax equals 0. And our column space is the set of all b's that satisfy b equals ax. Or in other words, it is the linear combo of the elements and the vectors of A. So to determine if U is in our null space, all we need to do is multiply A times U and see if we get the 0 vector. Right? So for 1, if I take A times U, do I get the 0 vector? Well, I want you to try it and see what happens. But spoiler alert, yes, I get the 0 vector. Now, is U in the column of A, or the column space of A? Well, remember that the column space of A is a subspace of R sub M. Nope, let's try that again. R sub N. And the null space is a subspace of R sub M. So that would mean in order for U to be in the column space, U would need to be in R3, but U is in R4, so not in the column of A, the column space of A. Same thing with V. Hopefully you can already tell that I can't even do A times V. That's not U, A times V, right? That's not even possible. So because it's not possible, obviously, it's not the, it can't be true. So it's not in the null space, right? I can't even do that multiplication. So my sizes don't match up. And then to figure out if V is in our column space, what we would need to do is take our augmented matrix and make sure that we have a consistent system for the augmented matrix with V, right? So essentially we're checking to see if this is a B that satisfies this solution. And it turns out that yes, this is consistent. So I'll let you verify that for yourself. But yes, this is consistent. So V is in the column of A, or the column space of A. So just some fun facts here. Try these out. So to give them a gander when you get a chance. I'm not going to talk through them, but these will help compare and contrast the null space and the column space, and how they can sometimes seem the same, but they're not. Right? They may have some overlap in terms of, depending on the size of A, they may have some overlap in terms of elements that are in each set, but they're not necessarily, or very rarely are they ever going to be the same subset. Hopefully that makes sense. Could I say that more times? Okay, let's talk linear transformations and how we can take this idea of subspaces to talk about linear transformations. So we defined linear transformations before as taking two vectors, as long as the transformation takes the sum of two vectors and it's equivalent to the transformation of the vectors and their sum, then it was a linear transformation. And so again, so here we have these ideas that so this again means it's closed under addition. And this means that it's closed under scalar multiplication. And if we let C be 0, that's going to give us the 0 vector. So hopefully you can see that that W would be a subspace of V, and that this is true. Yay! So they're vector spaces. So I'm mapping one vector space onto another. We saw this before as Rn onto Rm or whatever it is, right? Depending on the size of things. So it's basically the exact same definition we had before, but instead of R's, we talked about V's and W's. So we're talking about it in terms of vector spaces. The kernel of a linear transformation is equal to the set of all x's such that T of x is equal to 0. So, that looks familiar. In other words, the null of A is equal to the kernel of T. So we say kr kernel of T when T of x equals AX, right? Because the null of A is equal to all the solutions for AX equals 0. And we define the kernel as T of x equals 0. So, ta-da! The range is the linear transformation, is the set of all vectors of the form Tx for some x and v. So again, we're solving for what makes it true. So when T of x equals, I'm going to call it C, then and AX equals B, we're solving for basically the same thing-ish. So as long as, so this is the column of A is equal to the range of T when our T maps A onto X, or maps X onto the transformation A times X. Ta-da! So, right, we're solving for, hey, this is equal to B, right, which we said was the definition of column of A. Ta-da! Just a nice, lovely little visual here. And that's it. We are done for the week. I'm sorry, it got a little squirrely there towards the end, but I hope you had a wonderful time watching these. So goodbye.